In this session, we are going to discuss pulse position modulation or PPM. As we have discussed in last lecture that in pulse amplitude modulation, amplitude of a pulse is a variable parameter. But pulse position modulation is most efficient technique as compared to pulse amplitude modulation and pulse duration modulation. So before pulse position modulation, we have to discuss what is pulse duration modulation. In PDM, that is pulse duration modulation, the duration of each pulse varies in according to the sample value of message signal. PDM is also called pulse width modulation or pulse length modulation. Important point is that in PDM, at the occurrence of leading edge, trailing edge or both of each pulses, modulating signal may vary with time. So to understand pulse duration modulation and then pulse position modulation, we consider a sinusoidal message signal MT and periodic pulse train as a carrier signal, having constant amplitude and width. Now, first we discuss pulse duration modulation wave. In PDM, the duration of each pulse may varies at leading edge or at trailing edge according to the message signal. And here we consider trailing edge for variation according to modulating signal MT. For positive half cycle of modulating signal, the duration of each pulse increases from the trailing edge. And for negative half cycle, the duration of pulses decrease from each trailing edge. So, in pulse duration modulation, the width of each pulse is the variable parameter. But in pulse duration modulated wave, due to long duration pulses, there is considerable increase in power that contain no information. So, it is wasteful for the transmission point of view. Now, if we make duration or length of each pulse fixed or constant, then we can save transmission bandwidth and increase the transmission efficiency. So we perform next technique that is called pulse position modulation or PPM. In this, the amplitude and duration of each pulse is constant, equivalent to the pulse carrier, but the position of each pulse varies. Here in PPM, the position of each pulse is at the leading edge of pulse duration modulated wave. So by using PPM, we have variable position that is according to the modulating signal MT, and this method is more efficient as compared to PDM or PAM. So in pulse position modulation, position is a variable parameter that conveys some information. But in pulse position modulation, the sample duration is not constant. Now, the expression of pulse position modulated signal in time domain is expressed as S function of t equals to summation n equals to minus infinity to infinity g within bracket t minus nts minus kp m function of nts, where kp is the sensitivity factor of PPM modulator that is measured in seconds per volt, and g function of t is the standard pulse, and here m function of nts is the sampled value of modulating signal mt at t equals to nts and measured in volts. So in the expression of pulse position modulation, the sample version of modulating signal, that is m function of nts, is used to modulate the position of each nth pulse from minus infinity to plus infinity. Here, important point is that the variable width of pulses in PDM get converted into fixed width and we get pulse position modulated wave. This modification is expressed by kpm function of nts, which having a unit of second. Because we know that m and ts is measured in volts and the unit of Kp is second per volt. So Kp into m function of NTS is measured in second. Next, for the generation of pulse position modulation, there is a probability of overlapping between different pulses. Because the sampling period is not constant for adjacent pulses that we have shown in PPM wave. So in order to avoid overlapping, the following condition must be fulfilled. The sufficient condition for pulse position modulation to avoid overlapping is g function of t is equals to 0 for mod t greater than ts by 2, that is half of the sampling duration, minus kp into mod of mt max, that is maximum value of modulating signal. So this is a sufficient condition that the standard pulse is 0 for time, that is mod t greater than half the sampling duration minus kp into maximum value of modulating signal. And this requires that kp into maximum value of modulating signal must be less than half of the sampling duration. Now we note some points. First point is, as kp into maximum value of modulating signal mt is close to half of the sampling duration, the standard pulse gt approaches 0, and as a result the individual pulse of ppm avoid overlapping with each other. Also, in order to recover the sample version of modulating signal perfectly, the above condition must be satisfied. And if message signal is band limited to W, then using sampling theorem, keeping fs greater than twice of W, that is called sampling rate, we can recover the original modulating signal from the ppm signal without any distortion. Next, we discuss generation of pulse width modulation and pulse position modulation signals. Initially, we take any arbitrary modulating signal mt and sawtooth wave as a sampling signal. Here, sawtooth generator is used to generate sawtooth wave of sampling frequency fs. Now, these two signals, that is mt and sawtooth wave, are passed through a comparator. Here, non-inverting terminal corresponding to modulating signal and inverting terminal connected to sawtooth generator. The output of the comparator is pulse width modulated wave, that is shown by a waveform. Here, comparator compares both input signals. When the instantaneous amplitude of modulating signal mt is higher as compared to ramp signal, then output signal of comparator remains high. Here, each pulse of PWM output starts with leading edge corresponding to the vertical line of sawtooth wave and remains high as long as the amplitude of modulating signal mt is greater than ramp signal, that is indicated in figure. For the first ramp, the pulse duration of PWM is narrow, and this duration will increase as amplitude of modulating signal changes from negative to positive half cycle. So, in PWM, the leading edge is fixed while the trailing edge varies, that is duration, according to the instantaneous amplitude of modulating signal mt. Hence, PWM signal is said to be trail edge modulated PWM. Now, in order to generate pulse position modulation from PWM, we use monostable multivibrator at comparator output. This monostable multivibrator has negative edge triggered, which means that the monostable output goes high for a fixed time corresponding to each trailing edge of PWM signal. So, in PPM wave, the width and amplitude of each pulse is constant, but the position varies, and the information is conveyed through the changing position of different pulses. Next, we are going to discuss demodulation of PWM and PPM signal. First, we discuss demodulation of PWM. The block diagram of PWM demodulator is shown in figure. Initially, PWM with additive noise is passed through pulse generator, which removes the effect of noise and regenerate PWM. This regenerate PWM wave is applied individually to ramp generator and reference pulse generator. At the output of ramp generator, we have ramp signal. The slope of ramp signal is constant, that is, proportional to the width of each PWM pulses. The output of reference pulse consists of pulses having constant amplitude and width along with fixed delay time. These reference pulses having trailing edge corresponding to the leading edge of regenerate PWM in order to have fixed delay time. Now, the output of ramp generator and reference pulse generator get added and the constant amplitude of reference pulse get changed. That is according to the height of ramp signal. This adder output is passed through the clipper circuit having threshold value. Above this threshold level, we get clipper output and the clipper output having variation in amplitude levels, hence called PAM signal. And in order to recover original baseband signal or modulating signal, we use low pass filter at the output of clipper circuit. Next, we discuss demodulation of PPM signal. Here, we cannot recover original message signal from PPM wave directly. Here, we first convert PPM to PWM and then use the method for demodulation of PWM. In this, at the receiver input, PPM wave with additive noise is passed through pulse generator as well as reference pulse generator. Pulse generator is used to remove noise and we get PPM wave of fixed duration or length, but the position of each pulse varies that convey information. Output of the reference pulse generator generates a reference pulse of fixed period. The PPM wave and reference pulse is applied to RS flip-flop with set pin having reference pulse. And due to set and reset operation of flip-flop, we get PWM wave. And with the help of PWM demodulator that we have already discussed, we get modulating signal.